All right, welcome. I was asking everybody how their math is because we're going to do a lot of math this week, okay? I'm sure you two will be fine with that. Today we're going to start our conversation on differential analysis of fluid flow. And if you can't see behind my mask, I'm actually smiling because this is a topic that I really enjoy, but not a topic that I'm good at teaching. So hopefully I will be able to convey all my information to you, and we will be able to use that information to be better engineers. Now, I've already warned you before, but I'll warn you again. This week, we're going to be doing a lot of equations, a lot. Our examples and problems will be very limited. So let's just be ready to write a lot. I'm going to try to keep a decent pace, but I also want to try to finish the material I have to finish in time so that we don't spend too much time with the semester on these derivations. So first thing I want to talk about is what is differential analysis, right? So differential analysis consists of analyzing systems by looking at their derivatives, right? Analyzing properties by looking at their derivatives. For example, if I want to analyze the position of a particle, it doesn't have to be a fluid, it can be anything, the position of any object, any particle, I could analyze each position at each point in time, but sometimes it would be easier to look at the velocity, right, the derivative of the position with respect to time in order to come up with relationships for that position. Likewise, it may be even easier to look at the acceleration of that particle in order to understand its position. And that's typically differential analysis in a nutshell. We want to study fluid properties, but we're going to look at the derivatives of those properties instead of the properties themselves in order to find those relationships. So we're going to define a couple of terms that we're going to use in these notes. So for every differential equation, and you'll learn this when you take the class, in order to solve the equation, we're going to need a set of initial and boundary conditions. So for example, you know that whenever you solve a differential equation, you end up having to integrate the equation, and you end up with an equation plus a constant. So in order to find that constant, you're going to have initial or boundary conditions. So when I say initial conditions, I mean properties that are dependent on time, fixed properties that are dependent on time. For example, let's say that I want to track the movement of a ball. If I hold it up at some height, I'm going to call this height capital H. So if I'm holding this ball up at a height of capital H and I just let it go, and I want to track its position, it may be easier, instead of tracking its position, to track its acceleration. Because if I let go of a ball, right, I just let it go in free fall, do we know the acceleration of that ball, assuming we're here on Earth? What is that acceleration? 9.81, right? Gravitational acceleration, good. So we can study the acceleration of the ball because that's only one value, right? In order to find the position, which would be multiple values across time. Now, when I say initial conditions, they are conditions that are dependent on time. In other words, conditions at the start of your analysis. So if my analysis starts at the instant I let go of the ball, what initial conditions do you think we know? So what properties do we already know at that point in time? The position, right? So we know that the position, and let's say this is at time equals 0, is what? H, yeah. What else do we know?
Initial velocity.
Yeah, the initial velocity. So the velocity at time equals 0 is what? 0. Good. And of course, we already know the acceleration at any time would be just negative 9.81. I'm going to try to refrain from units for this week, just because we're going to have a lot of variables involved, and I don't want to confuse variables with units. But you know that we're talking about meters per second squared. So these are initial conditions. Conditions, well, these two. Conditions that we know at the beginning of our analysis. A second type of known conditions are called boundary conditions. Now, whereas initial conditions depend on time, boundary conditions will depend on space. In other words, boundary conditions are known properties of fluids at a particular location. So let me give you an example. Let's say we have flow we're studying flow through a pipe. This is a very, very long pipe. So we're only studying a small portion of the pipe. My first question to you is the velocity the same at every point in the pipe? What do you think? If we're just studying some normal, real fluid flowing through a pipe, is the velocity going to be the same at every single point along the pipe? So if I take my velocity here, is that the same as the velocity here at the center?
No.
Why not?
Because friction.
Because of friction, right? Okay. So if we're looking at this in cylindrical coordinates, right? So we have our coordinates of r, theta, and I'm just going to call this x, cylindrical coordinate systems. Can you think of any boundary conditions for this pipe system? You said friction, okay? So how can we turn that into a boundary condition? Do we know the velocity at any point in that flow?
When the I can't remember what was it, the radius is like at max.
Okay. So the velocity at the wall of the pipe?
Yeah.
Okay. So what's the velocity at the wall of the pipe?
0.
0. Do we agree on that?
Yeah.
And no slip condition. Velocity at the walls of a surface is 0. So if we're going to call, let's say we're going to call this radius capital R, then perhaps we can say that our boundary condition is that the velocity when radius equals capital R is 0. And that's a good example of a boundary condition. It's not enough. We're actually going to need some additional boundary conditions for this system, but I think just by looking at it, this is as good as it gets, right? We can find out this boundary condition. There are others, but we're going to talk about those later. Let's look at a second example of a boundary condition. Let's say we have flow in an open channel, and this time instead of drawing it in profile view, I'm going to draw a cross-sectional view. So we have flow on this open channel, cross-sectional, so traveling into the paper. What do we know about any fluid property? And this time, let's not think of velocity. Let's think of some other fluid property. Is there any other fluid property that we know at some point in this cross-section? This is open channel flow, right? Sorry? Pressure where? Pressure at the surface, right? What is the pressure at the surface?
0.
Atmospheric pressure, right? Or 0. Good. So we can write this boundary condition. Let's call this our channel height. Just call it h. And we can say that the pressure at any h is equal to atmospheric pressure, or 0 if we're dealing with gauge pressures. So those are examples of initial and boundary conditions. And you'll notice that whenever we want to solve a differential equation, we'll need these conditions to create our equation. Otherwise, we'll end up with a bunch of constants of integration. Any questions up to this point? I think we're reviewing stuff that I think we've already seen before. And if we haven't, it seems like this is something that we can understand, right? Initial conditions depend on time. Boundary conditions depend on space. So any questions with this topic? No, good. Let's review a little bit about what we learned in week 5, chapter 3. When we talked about introduction to fluid dynamics, we looked at velocity as a vector. I think you may remember that we described the velocity vector. I'm going to write this review. We looked at the velocity vector as being dependent on an x component, a y component, and a z component. Do we remember that velocity vector formulation? Good. Now we said that in a Lagrangian viewpoint, velocity only matters with time because changes with time because we're looking at a fluid particle and focusing on a fluid particle. But in an Eulerian framework, our velocity varies with time and with space because we're looking at a space of fluid, not at any one specific particle. So velocity is a function of space and time. But we also know that space, in other words, the coordinates of velocity, are functions of time themselves. Then how do we calculate the acceleration of a flow? Well, we know acceleration is dv dt, right? The derivative of velocity with respect to time. But velocity doesn't just depend on time. It depends on space, and the space coordinates depend on time. We said that we can calculate that acceleration by using the material derivative. Forget me mention that if we were to apply the chain rule, we would find that the velocity is a function of not just time, but also, my bad, you could find that the acceleration is a function of not just time, but also a function of the change in velocity with respect to space as that space changes through time. It's a lot of words there, but essentially what we ended up with in our discussion in week number 5 was that the derivative of velocity with respect to time, which we call the material derivative, was going to be equal to the partial derivative of velocity with respect to time plus the derivative of x with respect to time times the partial derivative of velocity with respect to x. And of course, we continue this expression with our y and z coordinates. Ethan, what do you think the last term I'm missing would be?
W.
Exactly. W.
And then partial B.
That's correct. Good. So essentially, this is the acceleration in vector form. It's a derivative of velocity that follows a fluid particle through a control volume, through an Eulerian framework. We call it the material or substantial derivative because it follows the particle, but through an Eulerian framework. It's kind of a combination of both the Lagrangian and Eulerian frameworks. Now, this acceleration is going to be important because we're going to keep using it in this class whenever we derive equations. Notice that I wrote these velocity vectors in red, and the only reason is because I want to let you know that this material derivative, capital D over capital DT, can be applied to any fluid property as long as it follows a particle. So you can not just have the material derivative of velocity, you can have the material derivative of density, for example, or any other fluid property. So let's keep that in mind, that this is a material derivative, and this operator can be applied to any other fluid particle as long as that particle moves through space and through time. Notice that this material derivative is a total derivative, but we have these squiggly derivatives here. Do you know what these squiggly terms mean? This Dow, partial derivative, right? And what's the difference between a partial derivative and a total derivative?
Partial derivative, you take this term, like x and y only, and z only.
Exactly. So when a partial derivative, just like Harry said, we look at only one, right, changing variable, right, each term. And we set everything else to be a constant value. So the partial derivative tells me if everything else, so for example, the partial derivative of velocity with respect to time says, if everything else, x, y, and z are constant, how does velocity change with time? And the same applies for all the other partial derivatives. I know we may not have dealt with partial derivatives before, so let's do an example. So let's say, and I hope, did you all have time to copy the acceleration equation? Okay, good. So let's say that we have a velocity field. And try to copy this example because I'm using a different book today. So let's say that we have a velocity field that's described by the following equation. My velocity field will be equal to x squared plus z squared multiplied by t I vector plus y squared minus z multiplied by t j vector plus x minus y k vector. And like I said, this week we're going to try not to focus too much on units. We want to focus on the actual operations, and later we can start adding units. This is the velocity of a fluid particle, or velocity field of a fluid body. Now my question is, what is the acceleration of this fluid body? And my second question would be, what is the velocity at point 1, 4, 2? So x equals 1, y equals 4, z equals 2. and at time equals 1. And finally, what is the acceleration at that same point and at that same time? Okay, so remember this is x, y, z, t. Any ideas on how to find that acceleration? First off, what's the relationship between velocity and acceleration? Acceleration is the derivative of velocity with respect to time. Good. So we know where to start, right? We know that acceleration is the derivative of velocity with respect to time. But, of course, our velocity doesn't just change with respect to time, it changes with respect to space. So we want an expression of acceleration that can account for the acceleration of any fluid particle within that body in whatever position it is. So how can we find that acceleration?
When we use the equation we had before,
Yeah.
where we take the partials like times x, y, and z.
That's correct, right? We find the material derivative of velocity with respect to time. And of course, we already learned that the material derivative was going to be equal to, I'm going to keep writing it and writing just so that we get used to writing it. So it'll be equal to the partial change in velocity with respect to time, the change in x position with respect to time, times the partial change in velocity with respect to x, the change in y position with respect to time, times the partial change in velocity with respect to y. Emily, can you finish this equation? What am I missing?
The W with the partial derivative of velocity over z.
That's correct. Yep. And this is our material derivative. Now my question is, do we know all these terms? Do we have everything we need? And when you have a large equation, I think it's just best to just start from left to right, figure out what we have, figure out what we need. Let's start with the first term. My temporal acceleration, my change in velocity, partial change in velocity with respect to time. Can we find this partial change in velocity with respect to time? What do you think?
X squared plus z squared, I.
There we go. Let's do it. Partial change in velocity with respect to time is, can you say that again?
X squared plus z squared.
S squared plus z squared I.
Yep.
What else?
Plus y squared minus z.
Plus y squared minus zj. Yeah?
That's it.
That's it. Does everybody agree with Harry? Is that the partial change in velocity with respect to time? Okay. Let's move on. We need the x component of the velocity. In other words, we're going to need the change in x with respect to time. Now, what is that x component? That u. What is that x component u equal to? Remember, we express the velocity vector as an x component, a y component, and a z component. My question is, what is the x component here? There we go. X squared plus z squared t. It's a scalar, right? We don't need the I vector. Does everybody understand why u equals x squared plus t squared plus z squared t? Or does anybody need a refresher on this? Are we good?
Could you explain it?
Yeah, sure. The velocity vector, right? I'm going to use a different color. The velocity vector consists of, in Cartesian coordinates, consists of three components, right? Any movement in the x direction, any movement in the y direction, and movement in the z direction. So we call those u, v, and w, okay? In this case, my movement in the x direction is defined by this equation, x squared plus z squared t. Now you may be a little bit confused because you think, oh, this is movement in the x direction, but I see a z here, I see a t here. All that means is that my x direction velocity varies with x position, z position, and with time. Think of it this way. If we're looking at flow in a pipe, and this is just a aside, okay? This is not related to this problem. If we're looking at flow in a pipe, you know that the velocity at the walls of the pipe is 0, right? And we know the velocity at the center is the highest velocity. The velocity profile will look something like a parabola for a Newtonian fluid. So we can plot the velocity in this way. Now for flow in a pipe, we're looking at incompressible developed flow. We're going to talk about what all that means later. The x component of the velocity, which is just a component along the center line of the pipe or along the longitudinal direction of the pipe, varies with what position? I'm just going to give you some coordinates here. We have x, we have y, z would be normal to the board. So my question would be, the x component of your velocity, just for this slice of fluid that we're looking at, this two-dimensional slice, varies with what variable? With y, right? Because as y changes, your x component of velocity increases, right? As y increases, it increases, and after the center line, as y increases, it decreases. So x component, just for this slice of fluid, varies with your y direction. So what that means is that just because it's the x component of velocity doesn't mean that it has to be a function of x. It can be a function of anything. Because all that tells you is, if I move upwards, I'll be moving faster in the x direction, which is what happens here. If I move downwards, I'll be moving slower in the x direction. So my x component of the velocity, my u, is going to be a function of y. Hopefully that clears it up. If not, we're going to keep practicing, so we'll get it eventually. Let's look at the partial change in velocity with respect to x. Do we know that partial change in velocity? All right, can anybody tell me what that partial change in velocity with respect to x is?
2xti.
2xti. What else?
Well, 1k plus k.
Plus k, good. Does everybody understand how we landed at this expression of 2xti plus k? Okay. Let's look at our v or y component of the velocity. What is v in this system?
Y squared minus z. T times c.
Exactly. Y squared minus z times t. Let's look at the partial change in velocity with respect to my y position. Harry, you're doing a great job, but let's let someone else try this out this time, okay? Can anybody find the partial change in velocity with respect to y?
2y tj minus k.
Yep, 2y tj minus k. So everybody understand how we got to that expression, 2y tj minus k? Yeah? Okay. So when I say the partial change in velocity with respect to y, what I'm asking for is the derivative of this expression if everything other than y is a constant. Okay? So if we treat x, z, and t as constants, and we only find the derivative with respect to y, notice that here we don't have a y. So if we don't have a y, we treat this as a constant. What's the derivative of a constant? 0. Right? Here we have y squared multiplied by t. So the derivative of y squared times t is just 2yt. Right? And here we have negative y multiplied by the k vector. So the derivative of negative y is just negative 1. So I get 2ytj minus k. So this is the same as saying 2ytj plus negative 1 times k. That's all we're doing. Does that make sense? Okay. The z component of my velocity field is?
It's just x minus y.
That's correct. And finally, the partial derivative of my velocity, I'll write this here, the partial derivative of my velocity with respect to my z position is what? 2zti, yeah? Close, you're very close. Minus what? Minus tj, good. You forgot that t, but it's okay. Any questions with how we found these derivatives, how we found these components up to this point? Notice that these partial derivatives, all we're doing is setting everything as a constant except your derivation term. Okay? Everything else is a constant. So far, so good? I'm trying to keep a steady pace, right? But I need you to let me know when you don't understand, because everything we're going to talk about builds on what we just did. So we need to make sure everybody understands before we... I say, you should know this, right? If your foundations are not good, your house is going to fall. Okay, so everything good here? All right. So let's move on. So this is an idea of how to find, right, the acceleration with respect to the velocity field. Now, they asked us to find the velocity at position 142, coordinates 142, and time 1. So don't try to overthink it. It's easier than it seems. What is that velocity? Or how do you find that velocity? Exactly. Just plug in those numbers. So let's go ahead and try to find that velocity. The velocity at 1421 will be equal to, well, we have x squared, and we said that the x position is 1. So 1 squared plus z squared. We get the z position is 2. Multiplied by time, and we get the time equals 1. In the x direction. Plus, what's next?
4 squared minus 2 times 1.
Thank you. In the y position, oops, I wrote k, it should be j. What else? 1 minus 4. 1 minus 4 in the z position. Okay, good. At this point, I think we can all solve this, right? Yeah. Great. So what do we have? We have 1 squared plus 2 squared, that's 5, right? Mm-hmm. So we get that the velocity at this point is 5I, plus, here we have 4 squared minus 2, that's 14, right? Okay, so plus 14j. You have plus 1 minus 4, that's negative 3, right? So minus 3k. And this is my velocity of the particle at point 142 and time equals 1. That means that in the x direction, my velocity is 5, whatever my units are, let's call them meters per second, 5 meters per second. In the y direction, my velocity is 14 meters per second. In the z direction, my velocity is negative 3 meters per second. If I were to ask you to plot an arrow showing the direction of this fluid particle at this point and this time, can you do it? Good. We're not going to do it, but I can trust that you can do it. Okay? Let's find the acceleration at point 1421. And for that, I guess we got to finish deriving our equation for acceleration. So we get that the acceleration of a fluid particle will be equal to the partial change in velocity with respect to time. So that is, and like I said, we're going to write a lot today. So that is partial v over partial t, dou v dou t, x squared plus z squared I, plus y squared minus z j, plus the product of the x component of the velocity and the partial derivative of velocity with respect to x. So I get the product of x squared plus z squared t multiplied by this partial derivative, which is 2xti plus k. Remember, don't mix up your vectors, right? Vectors, you cannot multiply vectors with themselves. You cannot add vectors with themselves unless they're in the same direction. So let's keep that in mind. Good. We have plus the y component of the velocity multiplied by the partial derivative of velocity with respect to y. So we get plus, my y component is y squared minus zt. And all this will be multiplied by my partial change in velocity with respect to y, which is 2ytj minus k. I'm going to have to move on. Plus the z component of velocity, that's x minus y, multiplied by the partial derivative of velocity with respect to z, and that is 2z t I minus t j. Look at that pretty equation. Of course, we have three directions, right? Three vectors. So we can at least combine the scalars of the respective three vectors. So let's see what that looks like. In the x direction, I have x squared plus z squared. That's my I. I'm going to try to find all my i's. So what are my I terms here? I have this term. Do I have any other i's? Here. This multiplied by the coefficient. And this multiplied by the coefficient. I think those are all my I terms. Is that correct? Okay. So we have x squared plus z squared plus x squared plus z squared times t times 2 times x times t. Right? This is this entire term. Plus x minus y times 2 times z times t. It's a big term. And all of this multiplied by my I unit vector. That's just one component of the acceleration, right? Let's find the remaining components. We have all this in the I direction plus our j direction, which would be y squared minus z. This is this j component. I have this j component, which is 2yt multiplied by this coefficient. So I will get plus y squared minus z times t times 2 times y times t. And I have one more j component, negative tj multiplied by the coefficient. I'm going to move the negative so that we get minus x minus y multiplied by t. And all this multiplied by my j unit vector. And finally, we get our z direction vector, which would be my k unit vector, which would be this vector times the coefficient, this vector times the coefficient, and I think that's it. Correct me if I'm wrong, but I think that is it. So we get x squared plus z squared t multiplied by k, so that's it, by 1, minus y squared minus z t multiplied by 1, and that's it, all this by k. Ooh, it's a lot, but I hope that we can appreciate that after this point, it's a simple math equation, right? It's a simple arithmetic equation. We just multiply things, factor things out. So what does that look like? Somebody just plug in, give me that final answer. Let's see, we got x squared plus z squared, blah, blah, blah. What?
Never mind. It's too much work.
Too much work?
Yeah.
That's fine.
I tried to combine the like term together, and it's too much.
It is too much work. Yeah. How about we do this? Why don't one of you find the I component, one of you find the j component, and one of you find the z component, and another group of 3 person confirm. So I'm going to give you your I component, Emily, I component, you confirm his answer. Jose, j component, Isaac, j component, you confirm Jose's answer. Harry, k component, Chase, k component, you confirm his answer. And while you're doing that, I'm also going to try to reorganize this equation to make it look prettier. How's that going, Ethan?
Yeah, I got an answer.
All right, can you give us that answer?
3i.
3i? All that work for just 3i?
Yep.
You confirm that?
Yes.
Jose?
Negative 95K.
Negative 95j. Isaac? Confirmed?
Negative 9K.
Negative 9k. Wow. That was a lot of work.
What about T though? Negative 9T? Or...
No, it's just no T.
T is just 1, right?
T is
Yeah.
because the combined lines come together.
All right. I'm not even going to try to finish it. So we found our answer. Essentially, this is how you find the acceleration of a fluid particle. And of course, all this assuming that we got all these derivatives correctly, right? And we plugged them in, everything correctly. It does give grounds for a lot of error, I admit. So which is why we need to be very, very, very careful when we deal with these derivatives, okay? Up to this point, we've talked about velocity and acceleration with essentially a review of Module 3, week number 5. Are there any questions with this topic? Everybody good up to this point? If I give you a bunch of velocity fields and ask you to calculate a bunch of accelerations, are we going to be okay? Okay. So now let's start this week's real topic, which is differential analysis, right? Let's actually talk about the differential operators that we are going to use this week. Now, when we're talking about functions that depend on space as well as time, or that depend on at least more than one coordinate of space, we're going to call those functions fields. In other words, if your velocity varies not just with x, but perhaps with y as well, we call it a velocity field. The condition for a field is that you should have at least two independent variables, or that one of those two variables is a space variable. Okay? So if my velocity varies with x and with y, that's a velocity field. It can vary with x, y, and z. It's still a field. So at the very least, two independent variables, and at least one of those variations has to be through space. Okay? Now, these fields don't just apply to velocity. They can apply to any other function, any other property. These fields are going to be the basis for how we study fluids. Now, you've already dealt with a field before, even though you may not have realized it. When we started fluid statics, we studied these forces acting on walls of a submerged fluid. Bless you. And we learned that the pressure at any one point in the wall would not be the same pressure at any other point at a different depth, right? We found that pressure acting on the wall of a submerged fluid varied with elevation, right? What was that expression that we found? That's correct. Where h is simply your depth. Now, how about instead of calling this my h-axis, I'm just going to call this my z-axis. I'll call this my x-axis. I'll call this my x-axis is my y-axis. Could you rewrite this expression in terms of one or more of these coordinates? What would p be equal to? X and y are horizontal axes. Z would be my vertical axis. Sorry? Yeah, gamma and z. But what are we missing?
X and Y.
No, we're not missing x and y. Think of it this way.
Would it be negative?
There we go. Why would it be negative?
Because are we taking like the origin at like the top of the circle?
Exactly, right? With z coordinate, with negative z coordinate, you increase your depth. You increase your depth, you increase your pressure. Therefore, my pressure is equal to negative gamma z. Now, believe it or not, this is a function, okay? And even though it varies only on this z term, we can simply express this as a function of gamma z plus 0x plus 0y, because there is no variation in the x and y direction. And when you look at it, what you have is a field of pressure. Pressure that changes as you move through space. We call this change in pressure, if we were to plot the pressure, we would have something like this. And we call this the pressure gradient. In other words, the change in pressure throughout space. So today we're going to figure out, or we're going to find how to find gradients for multiple functions, okay? So when I say the word gradient, I refer to the change of a property through space. Can you give me any examples of gradients? Any properties, any obvious properties that change through space? What do you think? Doesn't have to be fluids.
Atmosphere.
Sorry?
Atmosphere.
Yeah, atmospheric pressure, right?
Yeah.
Changes through different points in space. Any other ones that you can think of? I'm going to go with one. How about the elevation, the ground elevation? Right? You have mountains where ground elevation actually varies with space. So topography, right? A topographic map is essentially a gradient of the elevation component with respect to the x and y coordinates. So any property that changes through space, right? We're going to call it a gradient. So we're going to call a gradient the change of that property through space. And you'll find that calculating the gradient is actually very straightforward. Of course, if you look at this expression, you know that the gradient of pressure is simply going to be the change of pressure with respect to space. Can you find the change of pressure with respect to my space coordinates here? Let me express this in calculus terms. Can you find the derivative of pressure with respect to a space coordinate? What is that derivative? Well, negative gamma. Yeah. We have the derivative of pressure. What's my space coordinate? Z. What's the change of pressure with respect to Z? Negative gamma. That is a gradient. It's actually very straightforward. Now, you'll find that it starts to become a little bit complicated when your pressure doesn't vary just with one coordinate. It varies with multiple coordinates. But it's not that complicated. So it's going to look complicated, but it's not. In order to find that change, we are going to use an operator. An operator is any mathematical, I want to say any mathematical operator, but this is circular reasoning. An operator is a mathematical thing that causes a change to a variable that it is affixed to. The most common operator that you've already seen before is the d over dt operator. This is simply the derivative with respect to time. So how is an operator different from a variable? Well, if I apply this operator to a function, I'm going to call it f, df over dt. Let's say df over dt equals 1. Just an example, right? I can't divide both sides by f and get d over dt equals 1 over f, right? We cannot do that because operators are affixed to their variables, to their quantities, okay? So that's how operators differ from normal variables. Operators are linked to their quantities, so you can't really separate them. Of course, we know that we can separate the operators from themselves, right? We can move dt to their side, integrate, find the solution, but we can't separate d over dt from my function f, right? That's what I mean when I say operator. It's a quantity that is affixed to your function. You cannot separate it from them. So this is just an aside. So we find the gradient with an operator that we're going to call del, the del operator. I read through your book, your textbook, and I don't think your textbook covers the del operator, so try to take notes, okay? Now the del operator is represented with the character nabla, and this character nabla essentially represents an operator that will give me a gradient of a function. Now how does that work? This is an operator, remember, not a variable, an operator. So it needs to be affixed to some function, right? So this nabla operator affixed to a function, let's define a scalar function f, where f can be anything. Well, whatever, some function, some equation. If I were to take the gradient of f, in other words, if I were to apply the del operator to my function f, the result will look as follows. You would have the partial derivative of my function f with respect to x in the x direction, plus the partial derivative of f with respect to y in the y direction. Can anybody guess what comes after that?
Partial f over partial v and k dx.
That's correct. This is the gradient operator, also known as the del operator, also known as nabla. The gradient operator, when we apply it to any scalar function, gives us the change of that scalar function with respect to space. Now, it's got to be very clear, the gradient operator can only be applied to scalars. But the output, the result, is going to be a vector. So the input is a scalar, but the result, the output, is going to be a vector. Sometimes, because we want to express the operator in more general terms, you'll see that we have the expression of nabla by itself equals partial over partial xi plus partial over partial yj plus partial over partial zk. And this is a very, very common way of expressing nabla. But remember, this is not just any vector, right? It's not a vector with a magnitude of dou x. It's not. It's an operator. In other words, this cannot exist on its own. It needs to be affixed or combined with a function. Okay? So the gradient operator, right, gives us the change of a fluid property or any property with respect to space. Now let's see if we know how to apply it. Let's look at an easy example. I'm going to define the pressure field of a hydrostatic fluid with the following function. P equals negative gamma z. And I think we're all familiar with that equation, right? This is just hydrostatic pressure equation. My question is, what is the gradient of P? In other words, what is del P? Any ideas? First off, when I say del P, what am I saying? What am I trying to express physically? The gradient, right? And how do I find that gradient mathematically now? Use the formula. Okay, so let's go ahead and use the formula. We get that del P, in other words, the gradient of P, the change of P with respect to space, is going to be equal to the partial derivative of my function with respect to x in the x direction. So I get the partial derivative of my function pressure with respect to x in the x direction, plus the partial derivative of my function with respect to y in the y direction, plus the partial derivative of my function with respect to z in the z direction. And now let's solve for this gradient. What's the partial derivative of pressure with respect to x? What's the partial derivative of pressure with respect to y? What's the partial derivative of pressure with respect to z?
Negative gamma k.
So we get negative gamma k. And that is the gradient of a hydrostatic pressure distribution. So del P, sometimes we say grad P, grad for gradient, equals negative gamma k. So everybody understand where that comes from? We're going to use the gradient a lot. We're going to find that these gradients are going to be very, very useful in determining how fluid properties change. So it's important that we understand this del operator so that we can apply this del operator to more complex functions. And let's just do that. Let's apply this del operator to a more complex function. Anybody have any equation, any function that you may want to find the gradient operator for? I know nobody's just thinking of, oh, and off the top of my head, this is my favorite equation. But any equations that you may remember? Otherwise, we can just make one up. Make one up? Okay. Let's find, I'm going to call it the Harry coefficient, named after you. How do you find your coefficient? And let's make your coefficient a function of space and time.
Okay, so x squared plus y squared times zt.
Times zt. Okay. Good. So now, if this is the Harry coefficient, my question is, what is the gradient of the Harry coefficient? Any ideas?
It's going to be 2x dt.
Okay, good.
Direction.
Good. So we're finding first the partial derivative of the coefficient with respect to x, right? And we said that the partial derivative with respect to x is 2x zt in the x direction. What else?
Plus 2y zt.
Plus 2y zt in the y direction.
J direction.
Yep. What else?
Shouldn't that be TK?
Plus x squared plus y squared t.
There we go.
X squared t.
There we go. Plus x squared plus y squared
Oh, okay.
t. Okay. And this is the gradient of the Harry coefficient. Okay? I think you understand there's no such thing as a Harry coefficient. We just made it up. Okay, so don't study it for the test. Okay, don't memorize it for a test.
But he don't answer the question.
I may ask that question. Any questions with this gradient operator? Do you understand how to apply it to a function? As long as you have a scalar valued function, you can apply the gradient operator. What if my property doesn't change with respect to f, with respect to space? For example, what if I am looking at a property, let's say velocity, and let's say velocity is only a function of time. Let's say I'm looking at a property, a velocity, and the equation is 5t. That's my velocity, 5t. What's the gradient of that velocity? 0, right? Because there is no derivative with respect to space. Does that make sense so far? Okay, good. So that's the gradient operator. Now, this gradient operator is actually, even though it seems very simple, okay, yeah, change with space, it makes sense. It's actually going to be a very, very powerful mathematical tool. And we're going to see it a lot in our study of differential fluid motion. Because this gradient operator, we'll see, is everywhere. Whenever we derive an equation, any equation for fluids, we'll see, oh, look at that. Partial xi, partial yj, partial zk. That's the gradient operator. So any equation that we derive, you'll find that it always has that gradient operator. And that's why we give it a name, because it's always there. Now this gradient operator, like I said, it's a very, very powerful tool because not only does it allow us to perform operations on scalar functions, we can also combine it with vector valued functions to create new functions. For example, if I take a vector valued function, and just for simplicity, I'm just going to call that vector valued function f, okay, just f. If I take a vector valued function f, and I would like to find the dilatation rate, right? In other words, the relative change with itself in space. That's the dilatation rate, the linear deformation rate, you can call it. You can actually find that linear deformation rate, that dilatation rate, with the gradient operator. And the operation that we use is del dot my vector valued function. And when you see that dot, that's exactly what we're talking about, the dot product. Say, wait a minute, it's an operator, it needs a function, how can there be a dot product? Well, notice that when we take the dot product of this del operator with a vector valued function, you end up with a scalar that depends on the gradient operator. So how do we solve this dot product? Well, even though it's an operator, we can treat it as a variable for the purposes of our calculations, and you'll see that we're going to end up with a coherent function. In this case, we mentioned that dot product would be the product of the x components of a vector plus the product of the y components of a vector plus the product of the z components of a vector. So if we look at my gradient operator, my del operator, what do you think is the x component of that del operator? Yeah, partial or partial xi, right? And then the x component of my function will be whatever the x component of that function is. I'll just call it f of x. In other words, this gradient operator, this operator taken as the dot product of a function becomes partial of fx in the x direction. And then we have the y component of your gradient operator, that's dou y, times the y component of the function. Now remember, these are not variables, so we're technically not multiplying, we're applying an operation. So this is not dou y times fy, it's dou y applied to fy. So even though we treat it as they were two vectors, remember, we're not multiplying, we're operating. Okay? Plus, and can anybody guess what the last term in this dot product will be? Exactly. Partial of function z with respect to z. Now this is what we call the dilatation rate or the divergence. And we'll find that the divergence is going to be a very important topic in fluids. Now we describe sometimes that divergence as del dot some vector valued function, or sometimes in mathematics we can express it as div f. They both mean the same thing. It's just different types of notation for different fields. In fluid mechanics, a very, very, very common thing we're going to see is a divergence of the velocity field. Because the divergence of the velocity field tells us the relative change in those three dimensions. And that essentially tells us whether the fluid is deforming or not. If a fluid is deforming, the greater the deformation, the higher the divergence. In other words, if we were to find the divergence of a velocity field, which is just del dot v, the greater the deformation, right, the bigger this number. And the smaller the deformation, the smaller this number. Now, I have a question. And let me write the equation here. Dou u dou x, dou v dou y, dou w dou z. I have a question. Do incompressible fluids deform? Do incompressible fluids deform? And when I say deform, I mean relative to themselves. I don't mean changing shape. I mean actually changing their volume. No, right? They're incompressible. They do not compress. So if an incompressible fluid does not deform, what is the divergence of the velocity of an incompressible fluid? Zero, because there is no deformation. So if there is no deformation for incompressible fluids, the divergence of the velocity field should be zero. And this is actually very interesting. Because before, we had to assume that a fluid was incompressible. We're dealing with water, we say, okay, let's take it to be incompressible. How do we get that? Well, we did some experiments at different pressures, and we found that the pressure didn't vary, didn't change the density, therefore it's incompressible. But what this tells me is that all I need to know is the velocity of the fluid. And if I know the velocity of the fluid, I can tell if it's compressible or incompressible. Which means that I can give you the velocity of an unknown fluid. You don't know what it is. You don't know if it's liquid. You don't know if it's gas. And I could ask you, from your engineering perspective, is this a liquid or a gas? Right? With just knowing the velocity. So if you know the velocity, you can determine if it's a liquid or if it's a gas. So that is the divergence, right? The divergence tells us the change, the deformation relative to itself. In other words, the growth or shrinkage, I don't know what to call it, but deformation relative to itself. That's one important property we're going to learn with this del operator. Another property we're going to learn, we learned about divergence, which is deformation. There's another property that we're going to take for this del operator. Just by following the trend here, can you guess what that operation will look like? Yeah, pretty much. So if we take the dot product of two vectors, right, the dot product actually tells us the effects of one vector over another, right, and that's divergence. But if we take the cross product of two vectors, remember, cross product tells us what is the rotation potential between the two vectors. In other words, the cross product tells us the effect of the difference in direction between the two vectors, the potential for rotation. So following that logic, the cross product of a del operator and a vector valued function is going to be called a curl. And it's going to tell us the rotative potential of that vector valued function. Now, of course, you know how to find a cross product, or I'm hoping that you do. And for this case, this cross product will be equal to the determinant of my del operator with my vector valued function. At this point, I know we did our cross product example a few weeks ago. Does everybody know how to find the cross product of two vectors? Good. We find it the same way for this vector, which would just end up with partial fz over partial x. And this is going to take me a while to write, so I appreciate your patience. Oh, partial y, here we go. There we go. Yeah. I was like, that does not look right. Okay. I'm going to write the third term on the bottom. Good. We call this the curl of a vector field. Has everybody heard that word before, curl? So do you know what it means? Curl? Like just curl your fingers, right? Just kind of like rotate, right? So curl represents rotation. In the case of a fluid, the curl of the velocity field of a fluid is also a very important top property that we are going to see in this class. And the curl of this velocity field of a fluid, right, gives us something very, very related to the rotation of a fluid. We call the curl of the velocity field of a fluid its vorticity. Okay? And vorticity tells us the rotation of a fluid. Now, we're not going to have time to cover it in this class, but in the notes, you'll see that once we derive our angular acceleration, you'll find that angular acceleration in differential form is actually related to the curl of a velocity field. It's actually 1/2 of the curl of the velocity field. So when you derive angular acceleration, you're going to end up with an equation that's 1/2 of these three terms, which means they're definitely related. Now, I have a question. My fluid particle is rotating. What I mean is, as it travels, it rotates, right? As it travels, it rotates, okay? What if my fluid particle is not rotating? What do you think the curl of the velocity field will be? Zero. Good. So for fluids that are irrotational, in other words, fluids that do not rotate, the curl of the velocity field, or the vorticity, is 0. Now, I'm not giving you these terms just because I want you to memorize them, but if you already know some properties of your fluids, then you may be able to apply these relationships to simplify your calculations. Okay? That's why I'm giving you that. It's not like, oh, let's memorize every single curl for every single. It's just knowing these things about fluids will allow us to apply these expressions and relationships whenever we're actually solving for a system. So those are our two special operators that we're going to use with this del operator. The divergence, del dot a vector valued function, and the curl, del cross a vector valued function. Remember, the divergence is a scalar because the dot product of two vectors is a scalar, but the curl is a vector because the cross product of two vectors is another vector. Okay? Any questions up to this point? Yeah?
So the fluid's not in rotation, it's gas, right? You can consider gas as well.
It depends on your particle. It doesn't have to be gas necessarily. It can be liquids. You can have irrotational liquids. So rotation and vorticity, they're not related to the phase of the fluid, or they're not dependent on the phase of the fluid. Now in this class, up to this point, everything we've studied has had no rotation. And it's for a reason, right? Because we don't want to
Yeah.
insert terms that we're not going to study yet. But as we move forward, we're going to start to look at the effects of rotation in a fluid. Now, somebody asked me yesterday, why does the curl matter, right? And yeah, so just to answer that question, it's a good question. Hurricanes, tornadoes, whirlpools, toilets, right? Why does the curl matter? Because rotating fluids are actually very, very, very important in nature, and we also find them in some of our home applications, okay? So curl, rotation. Divergence, deformation, yeah?
Just a random question, but like, does the rotation of the Earth affect curl of any fluid?
Yeah, of course. On the website, I have these like videos of the week, right? And at the very end, after like, if you go beyond the final exam, there's a video called, or there's a link called the toilet roll thing. And if you click on it, it's 2 different videos that you have to press play at the same time. And one is filmed in the northern hemisphere, one is filmed in the southern hemisphere, and they see, right? They look at how curl affects, how Coriolis acceleration affects the curl of a fluid field. It's a very interesting, very well done video by Smarter Everyday and Veritasium. So to answer your question, yes. And then you can look at that video. They'll explain it much better than I can. Okay. Whew. I know we've done a lot. I know that we've introduced a lot of new terms. We've introduced a lot of new operators. Hopefully, with practice and time, we're going to get used to them. But I would like to at least finish class by applying these divergence and curl concepts to an actual velocity field. So let's go ahead and consider a 3-dimensional velocity field. And for this example, I'll just tell you straight up, we're going to look at the divergence of a velocity field. So let's consider a velocity field that's defined by the following terms. So, in this case, actually not divergence, let's look at curl. In this case, what is, okay, the vorticity of this fluid? In other words, what is the curl of this velocity field? So question, what is the vorticity of the fluid? And of course, you know that vorticity just means the curl of the velocity field. So how do we find the curl of a velocity field? Yeah, you take the cross product of the 2 vectors. Now, this is not something that I would want for you to memorize, but it is something that you're going to eventually get used to doing as you keep solving more problems. But the curl of this velocity field should be equal, if I remember correctly, to partial w partial y minus partial v partial zi, right? Because w is my z component of velocity, v is my y component of the velocity. Then we have minus, and what do we have? Partial x?
Yes.
Okay. Minus partial u, partial z, j, plus partial v, partial x, minus partial u, partial y, k. So what does that look like? Well, we have the partial change in my w velocity. In other words, the partial change in my z component of the velocity. Can anybody identify the z component of the velocity? Yep, 2z squared, right? This is number 2. And what's the change of that component with respect to y? Okay. Can anybody identify the y component, the v component of the velocity? xz squared. And can you tell me the derivative of that component with respect to z? 2xz. Good. Can you tell me the derivative of the z component of the velocity with respect to x?
0.
0. Good. Can you tell me the derivative of the x component of velocity with respect to z?
Maybe 5xy.
Okay. Can you tell me the derivative of the y component of velocity with respect to x? Let's go with Mohammed. The derivative of the y component, the v component, the y component of velocity with respect to x. Let's try again. Which of these three is the y component of the velocity? xz squared, right? So what's the derivative of this expression, xz squared, with respect to x? So if z, y, any other thing is a constant, what's the derivative with respect to x? Help him out, Smith.
X. With respect to x, right?
Yeah. So,
Z squared.
there we go. Thank you. And finally, can somebody tell me the derivative of the x component of velocity with respect to y?
5.
Thank you. And so we have the curl or the vorticity of this flow, which is the curl of its velocity field, negative 2xzi plus 5xyj plus z squared minus 5xzk. And I want a follow-up question. Is this flow at any point irrotational? And if so, at what point is this flow irrotational? What do you think? In the coordinates, in an XYZ coordinate system, where is this flow irrotational?
0.
At 0, 0, 0, right? Because if you have x0, z0, y0, then the vorticity of this velocity field is 0. Any questions at this point? It's a lot of math to handle. Yeah, go ahead, Nikhil.
Wait, would it actually be 0 if it is only x? Because it's 0 minus 0, 0 minus 0, 0.
You have a z square here. So it would not be just x0 then. So in order for this flow to be 0, at least x and z have to be 0. So on the xz plane, yes. On the xz plane, this entire flow field is 0. Okay? Any final questions? It's a lot, right? And the problems will be a lot of writing, a lot of calculating.